Okay, I suppose one of the first places to start the discussion with implicit functions is to explain exactly what is an implicit function. So this is Mr. Nolde with Planet Numeracy. Thanks for tuning in again. I appreciate it. And we're going to be talking about implicit differentiation today. But first off, what is an implicit function? Up till now, we've dealt with explicit functions, something along the lines of this, where it's explicitly solved for x. I'm sorry, I just misspoke. Where it's explicitly solved for y. So it's in function form, right? Something we called function form back in algebra. So this is called explicit. An example of an implicit would be something like along the lines of this. X times y equals 1. That's an implicit function. So before we would have differentiated that, we would have rewritten this as y equals 1 over x. And then we would have gone a little bit further and said y is equal to x to the negative 1. And then we could use just the simple power rule to differentiate this. And we'd say, all right, y prime is equal to negative x to the negative 2. So that was what we had to do up until now. All right, so let's go to the next slide and let me ask you a question. Okay, here's an example of an implicit differentiation problem. We're going to go through term by term. So I notice that some of these terms have y's in them, so I'm going to have to make sure that I multiply by the chain on the inside. All right, so that's this y. So that just means I'm going to write dy dx next to that term. Minus 2y, and then I have to insert a dy dx because it's not an x. Minus 5 dy dx. And then the next term, this is an x term, so that's going to be just like any other garden variety. And then, of course, a negative 4, any constant, goes to 0. So the first thing we want to try to do is group all of these terms together. And the reason we're going to do that is we're going to factor out this dy dx. So if I did that, I would end up with something that looked like this. And then let's move this over to the right-hand side. So that would make that a positive 2x. So dy dx is being multiplied by something, and I only want dy dx. So I'm going to divide both sides of this equation by this expression. So here we go. Dy dx. 2x. Put him at the center of the numerator there. 3y squared minus 2y minus 5. So this is the implicit derivative of this initial function. And what you have to remember is that this will, if I typed in a point, an x-coordinate and a y-coordinate, it's, as long as it's on this function, it's going to kick back the slope of a tangent line to this function. So in a second, I'm going to show you one where we actually have to go and type that point back in there. Also be careful you don't waste any time trying to solve something that has no solutions. For instance, I could get, my pointer, I could differentiate this term by term, get a perfectly good looking dy dx. However, note that this is a negative. There is no number that when squared is negative. So if I pick any number for x and square it, it will be positive. Any number for y squared would be positive. And a positive plus positive is never going to give us a negative number. So we just would never differentiate that. Another one I've seen is this. x squared plus y squared. What if it was just 0? It doesn't have to only be a negative number. The graph of this equation is just a single point, right? It starts to look like a circle with the center at the origin, but the radius is what? Has no radius. So this function, actually it wouldn't be a function, but there's nothing to be tangent to. So be careful on these because sometimes they'll give you one that sort of looks like you should be able to do something with it, but you can't. Okay, so here's a trig problem that needs to be differentiated implicitly because of the x and the y inside the angle. So I have to treat that as though it were a product when I differentiate. So let's go ahead. And first term, that becomes dy dx. That's the derivative of y, right? dy dx. And that is equal to the cosine of the angle. And this is the chain, right? This is my g of x, right? F of g of x. I don't do anything with that until now. And I'm going to multiply it by the derivative of the first, which is 1, times the second, plus the derivative of the second times the first. I'm going to write it this way just so it's x dx, x dy dx already in this piece here. So a gut reaction might be to try to divide both sides by this, but what happens when I divide dy dx by a two-term thing, I have trouble at getting at this. So the trick here is to distribute. So we'd have two terms on the right-hand side. So I'd have y cosine of xy plus x cosine of xy. And then I'll put the dy dx here at the end. So now I've gotten this piece, the dy dx, detached from this, one-termed expression by making it a two-termed expression. So I can move this to the left-hand side and then factor out the dy dx. So dy dx, this is the dy dx that's already over here. And then I'm going to subtract x times the cosine of xy dy dx. And that's still equal to, let's see, y cosine of xy. So now we can factor out dy dx. Careful here, a lot of students will just write this, they would just write negative cosine of xy, and they would forget that there's a 1 here, because dy dx times 1 was dy dx. Now I have to say dy dx times this was cosine, x cosine of xy. So very important that we get this 1 in here. And that's equal to y times the cosine of xy. Now we can solve this, looks like, for dy dx. There we go. So y cosine times the cosine of xy divided by 1 minus x times the cosine of xy. So now I have a derivative in this, which will kick out a slope of a tangent line to the original function. So there we go. We have a look at the difference between implicit and explicit functions. here. And then we looked at a kind of a simple looking now one in retrospect. How to do the implicit derivative of this. Then we looked at, let's see, ones to be on the lookout for. This just graphed as a point, and this there is no solution for. So there's no sense wasting any time in looking at those. Then here was one where we had to use, I had to use the product rule, right? Product rule. So last one we looked at was kind of a little bit of a doozy if you didn't know how to deal with getting the dx, the dy dx out of here to down here. So next time I'm going to show you, you might be wondering by now, why do I have to use this? What's implicit differentiation for? And the answer is, it is used for related rates. Let me jot that down. Related rate problems. So those can be fun. They're for sure on final exams across the country. So the next video I put up here for you will show you a related rates problem. But in the meantime, if you got value from this, please go ahead and hit the like button. And if you don't mind, go ahead and subscribe to the channel so we can get the subscriber count up there.